All right, hi everybody. Oh my God, I'm on a microphone. My name is Elaine Juten. I work as a software engineer at Cars.com. Today I wanted to talk to you about pattern matching. Also, as a side note, I woke up today and chose to look like Steve Jobs, and I thought about that when I looked in the mirror, so now you get to think about that too. So pattern matching, that is a foundational concept that I really struggled with when I was learning Elixir a little over a year ago now. The concept makes sense. We're seeing one set of data that it matches another set of data, but I would consistently get PR review feedback or pair programming feedback of, well, you can use pattern matching on this, that, or the other thing, and get rid of all these if-else blocks. And if-else blocks were my babies in Ruby and Rails and JavaScript. I used them quite a bit, so I felt pretty uncomfortable, and as a perfectionist, it was really frustrating for me to keep kind of butting up against that if-else block wall. So during my learning process, I had two main questions that kept coming up. One was, what are the tools that I can use to effectively pattern match in Elixir? And two, why? Like, why would I want to? If if-else blocks were working, my tests were passing, what's so great about them? So that's what I wanted to explore in this talk today, to hopefully make things a little more comfortable for folks that are learning Elixir for the first time, coming from a different language, or just learning development in general. So one of the first things that I learned when going through the Elixir tutorial was that the equal sign is a match operator and not an assignment operator like I knew it in Ruby. So we're checking for a match of data on either side of itself, which makes sense. And it's different from assignment. Like with assignment, when you declare a variable, we're assigning a value to that variable. But with Elixir, when we declare a variable, we're binding that value to a variable. I'll talk about this a little more later. It's kind of complex. We're just going to skim the surface. But let's open up an IEX shell in our terminal and play around with this match operator theory. So here I have a variable x, and I'm binding it. I almost said assigns. I do that all the time. To the string cat. And when we hit enter, it's saying, yes, we've successfully bound this variable. We've got it. So let's test this match operator theory in real life, in real time, because I'm here. So we have the string cat, and we're matching it on our variable x. When I hit enter, the string cat is returned. This tells us this match was successful, because string cat is equal to string cat. But I want to see this match error that I've heard so much about. So we have the string dog matching on our variable x. When I hit enter, I get that match error. So match errors occur when the values don't match. That makes sense. So let's try another data type altogether. So here I have a tuple of OK and the string cat, because I think I'm smarter than a computer, and I'm going to match on the variable x. Okay, I'm not smarter than the computer. It gets a match error out here too. So when the values are different and when the data types are different, we get those match errors as well. But let's take a look at a couple of more examples with some complex data types. So we have lists and we have maps. So lists are pretty strict when used in pattern matching. We need to match the number of items or elements within the list, and the order has to be exactly the same. So I put an asterisk by the number of items in the list because there's sneaky ways you can get around that. We'll talk about that later as well. But let's take a look at another example. So here I have a variable list. I am binding it to a list of 3 elements, Henry, Otto, and the number 13. And let's do a pattern match on that. So here, I'm switching up the order. So I have Otto, 13, and then Henry. And when I hit enter, we get a match error again. So rearranging the original list elements will get us a match error. They need to be strict. That order needs to be the same. But I've said they were strict in their size as well, so let's check that out as too. So here I'm adding a fourth element to our list, adding petty at the end, and seeing if it matches with our original variable that we bound. And it doesn't, because lists are strict. We need to match on their size as well as their size as well as their order. So one cool thing about, there's many cool things about Elixir lists, but one that I really like is Elixir supports the matching of lists heads and tails. So here in this example, we have a list with a variable head, that pipe symbol that we've seen around, and a variable of tail. And I'm going to assign it to, or I'm not going to assign it, my Ruby's showing. I'm going to bind it to a list with 3 elements. And when I print out head, I get the first element in that list. And when I print out tail, I get a list with the remaining elements of our original list. So the variables don't need to be named head, tail for this to work also. We can have multiple, and we can also have multiple heads, which I think is pretty cool. So in this example, we have a list with the variable cat, the variable mouse, that pipe symbol, and then the variable dog. And we're binding it to a list of 4 elements. So when I print out cat, Otto appears. When I print out mouse, cheddar comes out. And then when I print out dog, remember it was after that pipe symbol, we get a list of the remaining elements from our original list that we set up. So this pipe symbol can be used in pattern matching, but it could also be used to prepend items to a list too. It looks pretty similar to the head tail. So I'm just creating a cat list variable, binding it to a list with 3 items, and then I'm going to add Penny to the front of that list. So I'm declaring a list with Penny, that pipe symbol, and then putting in the rest of my cat list variable. So that was lists. Now we have maps. Maps tend to be the go-to when we want to use key-value pairs. It's one of our associative data structures in Elixir, and it's kind of the Wild West of data types, which is good. Any value can be a key, any data type can be a key, and no ordering is followed at all. So let's take a look at a couple of examples. So any value can be a key, and there's no ordering. So here we have a map variable being bound to a map with 3 key-value pairs. I can print out in IEX by declaring the data type and then the key of the value that we want. So when I print out a map of A, Henry is returned, the key of 2, Otto is returned, and the key of Penny, the number 13 is returned. So maps will match on a subset of the given value, so we can add additional key values, remove some. As long as the keys in the pattern exists in the map, we can get a match. So here I have my variable map. What if we matched with a map in a different order? So I switched up the order a little bit from our previous setup of the variable map, and I'm saying, hey, is the key of A within this map? And we get a successful match. Here, again, I'm switching up the order even more. So the keys of Penny and 2 are switched around, and again, I get a successful match. So as long as the keys we're matching exist within the map, we can get a successful match, and we don't get a match error. So here I'm looking for the key of C. Within this map, we don't have that, so I get a match error. So as long as the key is within that map, we'll get a match, but if it's not, we're going to get an error out. So let's review the ways that we can get the various match errors that we've seen. So when the values don't match, we'll get that error. When the data types don't match, when the data types are of different sizes, and when the keys in a pattern don't exist. So I promised I'd come back to this binding versus assigning business. You may have heard that Elixir has immutable data structures. Well, this is part of it. So when using the equal sign, or the match operator, we're always doing a pattern match that either succeeds or fails. Binding and assignment deal with memory allocation, but just like in slightly different ways. So with binding, the memory location moves, but the value stays the same, whereas assigning, the memory location stays the same, but the value moves. There's a lot more nuance to this. It could be 3 whole Elixir Conf talks plus, but if this sounds interesting to you, I say jump in that rabbit hole. It's, I dipped my toe in there, and then I realized I had a talk to give, and I should probably, continue with this. But yeah, it's really cool, the memory allocation business that goes on with binding. So, I covered a lot of information. So pattern matching can be used in simple or complex data types. Lists are strict in their ordering and size. Maps don't follow any orders, and keys can be any values. It's the Wild West in there. And match errors occur when the values or data types don't match, the data types are of different sizes, and keys within the pattern don't exist. So this is really cool. I'm really smart, I know. But how do we use these concepts on a larger scale, like in our actual code bases that we're working on or in work? And that's a good question. So in Elixir, we have a bunch of different pattern matching constructs available to us, but the 3 that I'm going to cover today are multi-clause functions, case statements, and conditional statements. So single functions in Elixir can have multiple clauses, and this is different than function overloading in some other programming languages, because functions in Elixir are identified only by their names and by their arity, or the number of arguments that are supplied to them. So let's take a look at an example. Here we have a module of animal, just like the example of Chris, with a sound function. We have multiple calls to the sound function, and Elixir will go in order from top to bottom, trying to find a match. And if none are found, we'll get a function clause error, but if one is found, we'll fall into that function and do whatever that code tells us to do. So if I were to call the sound function and supply a string of dog, we'll fall into that first match. We'll get a successful match, and arf will be returned. And if I call a sound function with the string of bird, we'll fall into that last function head, and caw will be returned. So multi-clause functions are a great way to help eliminate control logic. It streamlines the code into simple bite-sized pieces, which makes it easier to parse for yourself and for future devs. And then with that control logic separated out, it's easier to remove, refactor, add different function heads without much work. But there's a problem with this example. There's more animals than just these 3. So if we keep this function like this, we're just asking for function clause error after function clause error. And this is where the underscore comes in. So the underscore is typically bound to values that we don't really care about. We don't care if they match or not. And so I've added an underscore here within a function call to the bottom of my multi-class function list. Since Elixir executes from top to bottom, we want to keep our more general and default calls at the bottom of our multi-class function list. But I would encourage us to use defaults with caution. There are times we actually want to see these errors. We don't want everything to succeed. But for this case, I don't want to see any errors. So we have a little accessory to pattern matching, and that is guards. So guards allow us to be a little bit more complex with our matching checks. And it's through a defined number of expressions that can be used to ensure nothing goes sideways while we're executing our code. So when in doubt, I usually open up an IX shell in our terminal and test it out. If it blows up, then it's probably not a guard. But if it doesn't, it's a successful match, that's great. But there's also a lot of documentation around what can be used as a guard. So in this example, we have a cat module with a pet function, and we're supplying an age. So when the age is over 10 years old, we want to output to the user to pet that cat gently, because it might be frail. So the next thing are case statements. This is comparing one value against many patterns to help find a match. So here we have a housing module with a house or barn function, and it takes an argument of animals. And then we have a case statement with a couple of different lists within it. We have a list of cat, dog, and mouse that will output typically lives in a house. We have a list of pig, goat, and then there's that pipe symbol and that underscore. So remember when I had that little asterisk by lists are really strict in their size? This is the workaround. So with the pipe symbol and the underscore, again, it's similar to a head-tail declaration. We want to make sure that pig and goat are in that order. There are 2 elements to the list, but those could be the only 2 elements. There could be 40 additional elements after that. So as long as pig and goat are in that list, in that order, we will drop into this second case statement. So it's kind of cool. It can be used for bad as well as good, but I'm going to assume everybody's going to use it well. So if we get this case statement, we'll drop into typically lives in a barn, and then we have our default case statement that will catch everything else. Can't live in a barn or a house. I don't know, maybe a jungle. So let's test this out. So if I call the housing.house or barn function, and I supply a list of pig, goat, and horse, we'll get typically lives in a barn. We don't really care that a horse is in this list. Pig and goat are in this order. There are at least 2 elements. We're good to go, and it'll fall into the second case statement. So if we removed that default clause at the end, and we tried this out, and I'm supplying a list of turkey, ferret, and flying squirrel, so 3 animals that I never thought would be in a list, we get our case clause error. So the default function is really nice to catch these instances, but again, we want to use that with caution. Maybe we want to create another case clause that handles where turkeys, ferrets, and flying squirrels should live. But let's take a look at our third pattern matching construct, and that's conditional statements. It's used when we want to check multiple conditions and run code for whichever one is truthy. So here's an example. We have a conditional statement with 3 checks. We have if the string cat is equal to the string dog, if 2 times 2 is greater than or equal to 6, and if the tuple okcute is equal to the tuple of okcute. And that third clause that we have there is truthy, the rest are false. So we'll drop into that third clause and we'll get the output of yes. But what if all the clauses don't evaluate to truthy? So if all the conditions evaluate to false or nil, we get a conditional clause error. So if we wanted to avoid this error as shown, here we go. In the previous example, we might want a default case, but with the conditional statements, we can't just do an underscore. That default case is going to look a little bit different. So we're going to add a true. Since we're checking if it's truthy or falsy or nil, adding true here is the conditional statement's default case. And as we see, it works, falls into the fourth case because everything else is falsy. So let's review. So we have our multi-clause functions. A single function can have multiple clauses executing from top to bottom. So we want to put our most complicated matches first, and then move down to our general matches and our defaults. We have case statements that compare one value against many patterns. our conditional statements, which check against conditions and run whichever clause was truthy, only checking for truthy or falsy or nil. And then we have our little accessories. We have our guards, which can allow us to be a little more complex in our pattern matching checks. And then we have the underscore. We don't care about a value. It's kind of a default. And these are nice. These are great tools. But what happens if we come across if-else blocks in the wild and some legacy code, and how do we refactor that out? So let's take a look at an example. That's probably hard to read. It takes up a lot of the page, so let's zoom in a little bit. So here we have an animal module. We have our struct with a sound function. We're supplying an animal. And then we look at the animal type, and then sometimes we look at the animal age and we output a noise. So refactoring, this is our original setup. Looking at this, maybe let's refactor this down to still look at animal.type. I think that might be a good course of action. So let's turn this into adding a case statement and seeing if we can simplify this code a little bit. So that's the refactor with the case statement. I didn't do a very good job, I guess. It's a little better, but there's still some things that stick out to me. It's still pretty large. It's a pretty simple example, and it can become unwieldy pretty quickly. The more animals we add, the more different conditionals we add to make specific sounds. It can get pretty gross. We're still using nested if-elses, and ideally we would like to get rid of those. And the aardvark else statement can go away completely if we just refactored this again. So let's try to use multi-class function heads. We can start with our most specific, since Elixir goes from top to bottom with multi-class functions. So we have 3 options. We could do an aardvark, a cat, or a dog. I prefer cats, so we're going to do cat first. So here I am supplying a sound function with a type. We're expecting a struct with a type of cat and an age. And then I'm using a guard clause here. So when the age is over or equal to 10, we want to output meow. Feels pretty good. Okay, dog was pretty complicated. That can go next. So I'm adding another sound function with a struct, a type of dog, an age, and when the age is over 10, we get bark. So now we have the aardvark left with an age check. So I'll add that in here. So if the age is over 3, we want it to output squeak. I'm assuming that's what an aardvark sounds like when it's young. And if you notice in our smaller case statement, I've just removed that else case altogether. We don't need that anymore because it'll fall into our default. So now we can move on to our general calls. So I'm adding a bird, I'm adding a cat, the else of our original cat, adding a cow, adding the else of our original dog, and then this is our general catch-all default function. So as you can see, this to me is easier to understand what the function's actually looking for, but let's test it out. So let's say we want to get meow to output. I'll call animal.sound, I'll supply it with our animal struct, type of cat, and age of 13, and we get meow output. That's great. But taking a look at this default, I think we might be able to refactor it to be a little more strict, but let's again test it to see if we actually want that. So we expect an animal struct to be supplied to us, but what if the user is like, no? So I'm going to call animal.sound with an integer of 13, and it falls into that default. So this might be fine, but I think we want to make this a little more specific in order to prevent any random call from being successful. And this is a good opportunity to have those error messages help us in the future with additional features. If users are putting in numbers constantly without an animal struct, maybe there's something there that we want to add to tell the user to either stop it or to add a feature to allow for that. But we want an animal struct, so I'm just going to do like I did with all the other function head clauses and just add that struct in there and a type, and then we don't really care what type. It's going to be the general, but it at least constricts the user a little bit to input what we want. So let me test that out again. Animal.sound with the integer of 13, and we get a function clause error. But we can make this even stricter. Let's make that user work for this output. We specifically want an animal struct, so we can just declare that in all of our function heads. So I just changed that any struct to a specific animal struct, and that's our finished refactor. Could we refactor more? Probably, but that seems clear to me, and it seems more readable on this slide. So let's take a look at another example, a little more chaotic example. Yikes, oh my God. So first I would git blame. Just kidding. But this is a lot of code. It's a still fairly simple example. We're just, I can barely read it. We have a cat module with a feed function, and we're basically figuring out how much cat food to feed and what type of cat food to feed. So if we added any more complexity, this thing is gonna fall off the screen. And then taking a look within the if-else blocks, we have three main categories that we're looking for. So we're looking at the cat's age, we're looking at the cat's weight, and we're looking at the cat's appetite. So the cat's age seems to output whether we want wet food or dry food, and the weight and appetite are outputting how much food we're gonna feed to this cat. And so this seems like a great case to break apart this work into separate functions, even though Chris literally just talked about not doing that sometimes, but we're gonna do it anyway. So here I'm gonna strip back everything and just get to the basics. We know we want that cat module, we have our struct set up, and then we have this feed function to kind of act as our executor. So now we have two main questions. What type of food are we giving this cat? And how much of that food are we giving this cat? So let's go through type of food first, since we only need the age to figure that out. So here, I'm adding a private function of type of food. We're looking for the cat's age, and I'm gonna use a conditional statement. So if the cat's age is over or equal to 10, we wanna output wet food to the user, and then anything else, we're gonna output dry food. So since I'm doing a specific cat struct check, I feel comfortable using this default of true. So next, let's move on to finding out the amount of food we can give to the cat. So here, I'm creating another private function of amount of food. I'm supplying the cat's weight and appetite, and then I'm combining the cat's weight and appetite into a tuple data type. This is just to make that case statement check a lot easier, and we can match on this now. So if the cat is lean and strong, we want to output 30 ounces of food, lean and moderate, 25 ounces. Please don't actually feed your cat this amount, talk to your vet. Lean and low, 20 ounces. So here's what we have so far. We have our two broken out functions. That's great. So let's put it all together in our executor function. So here we have feed. We're going to supply the cat struct, age, weight, and appetite. And then I'm creating two different variables. I'm creating food type, which is calling the type of food function, and food amount, and then I'm interpolating them into a string. You can just call the functions within that interpolation, but that makes my brain explode, and it makes it really hard for me to read personally, so I broke this out to make it a little simpler. And this is our completed function. It's still quite a bit of code, but it's not, 3 rows on one single slide. So let me test this out. So I'm calling cat.feed. I'm supplying the age of 13, weight of normal, and appetite of strong. And we get 25 ounces of wet food. Seems to be working. But looking at this feed function, I think we can refactor this again. We can make it more streamlined. We're not actually using the elements within the structs that we set out. We're not actually using age, weight, or appetite, so I'm just gonna add that underscore. We expect a cat struct of age, weight, and appetite, but what those values are, we don't care. Our private functions are gonna handle them. And you know what? Let's get crazy. I'm going to bind this cat struct to a variable named cat. So now we have this cat struct within a variable, and we can pass this variable down to our other two functions. That streamlines the code a little bit as well. And I would feel a little comfier putting the type of food and amount of food function calls within that interpolation itself. But I'm not going to. I'm not getting that crazy. So this was what our final refactor looks like. As a reminder, this was our original. That's a lot of ends at the end. A lot of if-else blocks, and more importantly, there's a lot of different processes that are happening within this one function. So we wanted to try to break that out. So here, we've used our library of pattern matching tools to split out our processes and to make things generally easier to read. So, wow, that was a lot of information that I just went through in a short amount of time. So let's talk about some takeaways. So pattern matching is checking to see if both sides of the match operator match. We have multi-clause functions, case statements, and conditional statements. They help create more streamlined and easier to read code base. And then we can use our accessories of guard clauses, underscore variables, and pipe symbols to make it work for us as well. And then match errors occur when the values or data types don't match, when data types are of different sizes, and with keys within the pattern don't exist. And if you see some nested if-elses, I encourage you to refactor them. It's a great way to learn what other pattern matching clauses that we have within Elixir, and your future devs and yourself will thank you when you have to touch that code again. So that's it. Bye.